Okay, so welcome. So last time I was discussed the SYK model and some of its properties, and talked about a little bit about the consequence of the fluctuations from the large and mean field theory. Anyway, and today we're going to start a somewhat different topic, although there will be some connections, as you will see. But are there any questions? Many of the things that I talked about are written up in this review article that we've submitted to Reviews of Modern Physics, and that's linked on the website. Yeah, so I didn't prepare separate notes. But there's a new set of notes that I put on today on the topics I'll talk about today. Can you hear me online also? I forgot to check. Someone say hello online.
Hello.
Hi. Okay, great. All right. So these are the topics we'll talk about today. And as you'll see, this is quite a complicated subject, but in the end, there is an underlying simplicity, which is, I think, been understood only relatively recently. And on the other hand, however, it's probably the one topic that applies to the widest class of physical system. It's really extremely important in so many different contexts across physics in studies of modern forms of quantum matter. So it's something that really deserves to be understood very well if your purpose is to understand real materials that are actually out there. So the basic problem is to think about what are sometimes called non-Fermi liquids. So as we'll see, these are systems that have a Fermi surface, a well-defined Fermi surface, but there are no quasi-particle excitations. Or if they are quasi-particles, they're very weakly defined. We'll restrict our attention to two dimensions where, in fact, the quasi-particles are not present. So there's two broad classes of systems for which these kind of problems apply. One is if you take any Fermi surface, some set of fermions that have a Fermi surface, and couple them to a gauge field. And there's many different contexts where such problems arise. We've already seen a couple. There's a spin-on Fermi surface, where you take some spin system and you write the spin operator in terms of partons, which are fermions, and the partons have a description that gives them a Fermi surface. And the structure of the parton mean field theory is such that there is some continuous gauge field, continuous gauge symmetry, like a U1 or SU2 or something like that. So then you get a problem of a Fermi surface coupled to a gauge field. That's a spin-on Fermi surface. The other problem we talked about very briefly is the half-fill Landau level in the fractional quantum Hall effect. If you have exactly half-fill Landau level, then that can be written via the parton construction I talked about, again, as a problem of fermions forming a Fermi surface coupled to U1 gauge field. Another problem that I haven't mentioned, also of great importance, is the quark-gluon plasma that's studied at relativistic heavy ion colliders, Brookhaven and CERN. And so there you have a collection of quarks, which because of their high density and the high energies are deconfined. And then they form a Fermi surface since there's a finite density of quarks. And those quarks then interact with the gauge field. As we'll see that the gauge field is very strongly damped in all of these cases. So the assumption is that the confining force doesn't take over. Of course, if the confining force took over, then the Fermi surface would disappear. So just the fact that you're talking about a Fermi surface means that the gauge field is not confining. The other problem, the other class of problem, which are a bit simpler, but in the end reduced to essentially the same physics, are those where you have some kind of ordinary symmetry breaking in the presence of a metal. So, the only restriction is that the symmetry breaking order parameter be at zero momentum. So, for example, this rules out antiferromagnetism, which is at momentum pi. But it allows for ferromagnetism. And in fact, that's the example that I'll talk about. The antiferromagnetic case in the presence of a metal is also very interesting. We mentioned that a while back, but it has a somewhat different behavior, so I won't talk about it. And it's not as, and the non-Fermi liquid there is not as well defined. Okay, so case A under part 2, well, I should have written it over there, would be something like ferromagnetism in a metal, the onset of ferromagnetism in a metal. So right at the critical point, then you'll get a state of matter where quasiparticles are not defined, but with a Fermi surface. And there are, in fact, some recent examples in 2 dimensions where this could be studied, I think. Case B would be any kind of point group symmetry breaking. So you have some crystal which has a certain point group, say a square symmetry, and then it decides to become a rectangular symmetry. So there you've got a crystal going from a square shape to a rectangle shape. This is called nematic ordering, or Ising nematic ordering in the literature. So for example, and this has also been studied a lot recent years. It's, could possibly be present in the cuprates, but almost certainly present in the pnictides and so on. Yes, Subro.
But for the second class, you also don't want to break the yuan particle number symmetry. Like you don't think about superconducting transition.
Yeah, so that's right. So I don't think I've said super. Yeah, I mean, I think my statements are still correct. Okay.
Because the S wave.
All right. Okay, you're right. So this statement is not completely while preserving the Fermi surface. So preserving. I mean, that's implicit. Yeah, you're right. So I should say that. So if you're looking at the onset of superconductivity, that's a different beast because it breaks the U1 symmetry and destroys the Fermi surface. All right. So these are 2 broad classes of problems with in many different physical contexts. So you might despair, there's a lot to learn here. But fortunately, all of these systems, abelian gauge field, non-abelian gauge fields, these things with autoparameters, in the end reduce to the same basic theory. And I'll try to give you a summary of what that theory is and some of its properties, and try to, give a physical feeling for what's going on. So that's fortunate. Okay, so let me just begin by saying, what do I mean by a Fermi surface without quasiparticles? So, when we start out with free electron gas, then we learn about the momentum distribution function. You compute the momentum distribution function, and for a free electron gas, it's 1 below the Fermi wave vector and 0 above it. Then we put in interactions between the fermions, as we did in Fermi liquid theory, and then we found that, well, what happened was you still had a Fermi surface with well-defined quasiparticles, but the only thing that happened here in the momentum distribution function was that this discontinuity, which is related to the Z factor, was not 1. So in a Fermi liquid, you had a discontinuity in the momentum distribution function at the Fermi surface. And quasiparticles are very well defined. Now, there is one system which we didn't talk about at all, actually, mainly because of choice of topics. I mean, this is something I do cover when I teach this course in other years. And that's a 1-dimensional electron gas, sometimes called a Luttinger liquid. So in a 1-dimensional electron gas, there are no electron quasiparticles. There are these collective modes, these bosons, these gapless bosons that do in fact form the right quasiparticle description. But if you measure this n of k, then you would get a distribution function that's even less singular here. It doesn't have a discontinuity, but it does have some singularity. So I mean, there's some power law singularity without a discontinuity. So if you took enough derivatives at this point, it would eventually diverge. So this is n of k in orange for a Luttinger liquid. And so n of k near kf has some k minus kf to some power with a sign of k minus kf. Some singularity like that. So there's no discontinuity, it vanishes, sigma is a positive power, but there's still a Fermi surface, okay. All right, so that's an example of a Fermi surface where there are no fermionic quasiparticles. As I mentioned, there are some other bosonic quasiparticles that don't really live at this momentum, but anyway, that's a different story. Okay, so, and what about the electron Green's function that you see for a Luttinger liquid? Well, the Green's function is, say of the right moving fermions would be g of k and omega and k has some singularity again, which is 1 over omega minus vfk to some power. So this is sort of like a conformal field theory. We have the right moving fermions and the left moving fermions. Oh, sorry, I should explain what this k is. So this is, let me call it P. And this is your Fermi gas in one dimension. So now I'm focusing the vicinity of this point, and this is the coordinate k, this from this point. So on this point, you only have a right moving fermions, and this point you have left moving fermions, and they can interact and give you sort of the bizarre correlators of this type with the power law. And that if you take the omega integral of that, that leads to, this is some other power, not the same power, in the momentum distribution function. Okay, now there are actually a lot of discussions in the literature that if you go to higher dimensions, and in particular, Anderson certainly talked about this at various points, that a higher dimensional non-Fermi liquid without quasiparticles is just a version of a collection of these liquids in one dimension. So in higher dimensions, you have a Fermi surface, and the idea would be that if you went to 2 dimensions, which is what we are going to focus on, so in 2 dimensions, you have a kx and ky. With some Fermi surface of some strange shape. These are the occupied states. And then you pick a point on this Fermi surface, say this point over here, and you call this direction, let me again call it to be consistent, px and py. And if you call this k measured from the Fermi point, just like you measured in 1D, then if you looked at correlation function along this direction, you would get a singularity, which is similar to that thing that's partially obscured by the board. And this would happen on every different direction. So it'd be a collection of one-dimensional, chiral Fermi gases as you go around the Fermi surface. So that's an interesting proposal. And what I hope to convince you is it's just wrong. I mean, it's simply not what happens. The structure of the non-Fermi liquid in higher dimensions is simply not a collection of 1D gases. Now, might be tempted to think in terms of 1D gases because that's what you do in Fermi liquid theory. In Fermi liquid theory, you have free fermions moving along these directions, and they interact with each other weakly. So the Fermi liquid theory does look like a collection of 1D interacting gases. In fact, free fermions in that case. So you would say, well, you just take a Fermi liquid theory and give it some exponent sigma tilde, which is not the free exponent, and you're done. Well, at least that's a good starting point. And I only mention this because there's just so many papers that take that point of view. and that is not correct. Okay, all right. So what is, so let me just give you the answer. I mean, no surprise to experts in the field. What does actually happen? Well, so the better analogy, although it's not complete, is the SYK model. So what we learned in the SYK model was that the Green's function was, at low frequencies, G of omega, well, had a bare term, omega here. And then you got, with some prefactor, some square root of omega term. Okay, that's what we learned in the SYK model. There was a singularity which was purely local and just depended on a singular omega dependence. And for the non-Fermi liquid in 2D, what we're going to show is G of omega is very similar. So this omega term we drop because at low frequencies, it's much smaller than this term. But at high frequencies, you can keep it if you want. You're going to get omega minus VFK, where K is measured here, minus, again, some number with omega to some power. I call that A. So that singularity will be purely local. And this power, in fact, is 2/3, not 1/2. And that power 2/3, essentially applies to all these problems. It's the same power that comes out in the leading large N theory. There are corrections to this at higher order. They're not as well understood as the corrections are understood in the SYK model. That's still, very much a problem of current research. What are the corrections to this leading structure that comes out of, many different approaches, and I think pretty well established, I believe, the correct way to think about it. So all you want to do is take the SYK like Green's function and add a little K dependence to the local chemical potential, if you wish. There's a shift in the chemical potential, which is this omega minus VFK. So you can throw this omega out, but since this is the only K dependence, you can't throw the K out. You can compare, and the trade-off between these two leads to all kinds of interesting effects. All right, so that's what I want to, I will definitely get to this by the end of next lecture, maybe even this lecture, but that's where we're going. To show you the singular structure of the Green's function, and then also discuss some of the consequences for various physical properties. Okay, yeah, any questions?
So
is there an intuitive way to understand where the randomness in the couplings of SYK originate from, or is this something you will explain?
I'm not really going to talk about SYK. I'm going to talk about systems which are spatially translationally invariant today. SYK, there we just take, we took random couplings because the real world had random couplings. We were interested in describing random spin systems. We can also talk about the effect of randomness on these non-Fermi liquids. If I have time, I will say something about that. And that does change the structure quite a bit. But right now, my discussion is about non-random, non-Fermi liquids. I think the point here, however, is that there is still a connection because in the SYK model is essentially a point in space. It has no spatial structure, and so the Green's function is purely a function, purely local, only a function of a frequency. And remarkably, that's what happens here too. You start with a model which is fully translational symmetry, but the leading singularity is purely local. It doesn't have any K dependence. It's entirely in the frequency. And how that emerges is what I'm going to show you. How this locality emerges in a system that's fully translationally invariant. It doesn't quite map onto the SYK model because there's still this K dependence you have to keep, but there are some similarities. Yeah.
Thank you.
So the singularity that you just wrote down about this Fermi surface state in
Yeah.
2 dimension, this is different from the Latinger liquid type of singularities. Is it because this transverse scatterings are important?
Yes,
Is
yes,
that
yes, absolutely. The dominant scattering in a Latinger liquid, if this was a Latinger liquid, would be electron scattering from here to there. And that's what leads to that non-Fermi liquid behavior. As we'll see, the dominant scattering of an electron here will be in this direction, orthogonal to the Fermi surface. And when you put that all together, it leads to this rather local self-energy. That's a bit of a surprise, but I'll show you how that happens. All right, great. So let's get started. So there's various steps here. One is to pick a simple example and work with it. And then maybe by next time, I'll be able to show you why all the other models are pretty much the same. So I'll pick the example of the ferromagnet. And so I'll write down a definite field theory, and we'll try to understand its properties. Okay. Okay, so we're going to take a, Lagrangian, which will have, let's say, some fermion. It will have an order parameter, which I'll just take to be a scalar, plus some coupling between them. Let me call it Ly, because that's the Yukawa coupling. So the fermion part is just free fermions. I'll someone K and alpha. K is momentum. Alpha is spin, because I'm going to talk about ferromagnetism. D by d tau minus some dispersion E of K. So for now, I'm not going to go to any long wavelength theory of the fermions. Just keep all momenta across the Brillouin zone, and E of K is some arbitrary function of momentum. And of course, this means there's a Fermi surface, and the Fermi surface is just a locus of line where E of K is 0. So we'll essentially zoom in to the Fermi surface and take some kind of continuum limit to get a quantum field theory. But the whole task is to figure out how to zoom in. What's the correct way to write down the field theory? And it took a while to understand that. That's not an easy task, but I'll hopefully present it in a way that you can see that it's really the right way to proceed. So, one way to do it is, well, just linearize of these and write it as a bunch of infinite number of 1D chiral fermions. That doesn't work. That's wrong. Okay, so then there's a scalar field, which I will take the continuum limit because it's a 0 momentum order parameter. So right, so there's some delta phi squared, there's phi squared, plus some s phi squared plus u phi to the 4th. Okay, schematically. And now this order parameter phi, I'll think of as a ferromagnetic order parameter. So I'm imagining the following situations, that I have electrons with spin 1/2. I have a 2D metal, and I'm varying some parameter. In fact, I'm going to be varying s. So as s, and there's going to be 2 phases. When s is large and positive, then phi has 0 average. And the Fermi surface need not be spherical to have any shape. I'm just drawing a sphere, a circle. And it has equal numbers of both up and spin down particles. So they spin up and they spin down. And they both share the same Fermi surface. So the only symmetry I'm going to assume is spin inversion symmetry. So phi goes to minus phi. And so I'm assuming there's some spin orbit effect that prefers the z-axis. So I'm going to just, for simplicity, not worry about rotational symmetry in spin space. So this is really a theory for Ising ferromagnetism. So what happens on the other side is that phi condenses, or in terms of the fermions, there are more upspins than downspins. So now you're going to get two Fermi surfaces. There'll be the upspin Fermi surface, which becomes slightly larger. So this is upspin. And I'm going to exaggerate it. Then there's a downspin Fermi surface, which is slightly smaller. And okay, so these are the occupied states for downspins. And these are the occupied states for upspins. So my autoparameter phi is something like the number of upspin like fermions minus the number of downspin fermions. Okay. So both of these states, when you study them, are Fermi liquids with quasiparticles. Once you're in the ferromagnet, then there'll be quasiparticle excitation of downspins on this Fermi surface and another one on the other one. This is sometimes called, it's a metallic ferromagnet. Sometimes people talk about a half metallic ferromagnet in which one of these Fermi surfaces just disappears, but it need not. This is a very useful type of thing that used in spintronics all the time, where you have some kind of ferromagnetism developing in a metal, because then you can couple the flow of the electrons, the charge, to the spin. Okay. So what our interest today is to talk about this critical point. What happens right at this point where the Fermi surface is just about to split into two different sizes. So you might expect that right at that point that fluctuations of the fermions right on the Fermi surface are going to become very singular. You could try to write down a theory of, think of this as a surface and write down some string theory of the fluctuations of the surface. As far as I know, that hasn't been successful, but anyway, but that's roughly the picture. We're going to talk about the fluctuations of the surface in some systematic way. Okay. Of course,
just to clarify, this is all in 2 dimensions, right?
Yes, I'm going to talk. Well, the theory can be done in 3 dimensions too, and it's much less singular, and it's quite easy to understand using basically perturbation theory. But if you want to get some really non-trivial effects, you have to be in 2. Yes.
Okay, thank you.
Now, if this was the only theory, then of course we know the answer to this. This is just the 2 + 1 dimensional 5-fold field theory, the original problem solved by Wilson and Fisher, and you would write down some exponents and all kinds of stuff about this critical point. But that's not the answer, of course, because these 2 degrees of freedom are coupled, and the coupling is basically a coupling between these 2, the fermion side and the boson side. So G phi times F dagger alpha sigma Z alpha beta F beta. Sigma Z just a diagonal matrix 1 - 1. That's exactly this object here. And there it is. Okay, so this is the theory that we're going to study. Simple enough, it's just putting together a Fermi surface with a scalar field, with the simplest possible coupling, no gradients, nothing, just phi F dagger F. You would think this had been solved a long time ago, but it hasn't. It's still quite a complicated theory, and I'll try to show you what happens. All right, so everyone understand the problem we're going to address?
One clarification.
Yes.
In the first LF, in LF, F has momentum labels and phi has position labels, and in
Yes.
Ly, what are the labels? Is phi in K and F is also in K?
Yes, thank you. So I should really, so this is the full Lagrangian. So actually this is integrated over all space, d2x, not the Lagrangian density. And you integrate everything over time to get the action. And this is d2x here. And in this case, these are phi of x, f of x, phi of x. And of course, the relationship between f of x and f alpha of k is the usual Fourier transform. But this Fourier transform has to be done in the Brillouin zone. You can't, right? You're right. If I still have a Brillouin zone, then this should be a discrete sum over lattice sites, because if I have a Brillouin zone, then x is discrete. Yeah, so you can think of this as just a schematic way of representing a discrete sum. Right, okay. Yeah.
And this would be different from phonons coupled to Fermi surface, because that would have an extra gradient.
Yes, yes.
And that would make it irrelevant.
That's right, yeah. So there would be an extra gradient here. Right, yeah. Okay. All right, so you can imagine this kind of theory has been studied a lot, and it has in many different forms over the years, in many different methods. So one method is to just do perturbation theory in G, do some kind of renormalized perturbation theory in Z. You get some set of answers, but then you find all kinds of singularities, and you have to do some RG and wave your hands and get some results. Another method is to give the fermions this alpha index. Instead of running from 1 to 2, you let it run from 1 to n, and then you take some large n limit. And that actually is reasonably successful. It gives you some set of answers which in fact are correct. But then when you try to look at higher order corrections, as Sung-Sik Lee showed, you run into a lot of serious issues. There is that particular one of n expansion not well defined. So what I want to present is a new set of ideas where you get two things. One, you get an action whose saddle point gives you immediately the correct, the leading low energy behavior, you believe. And once you have a saddle point in some large n limit, then you can at least think about how to systematically do 1 over n corrections. So all the previous methods, for all their virtues, don't give you any systematic way of understanding what the correction to your answer is, at least in principle. I'm not going to actually compute those corrections. That's extremely hard. It's even harder than the correction for the SYK model. But at least in principle, I think there's a lot of virtue. What we've learned is there's a great virtue to having a saddle point. If you want to define a theory properly, you should have a saddle point. So how do we get a proper theory for a saddle point for a theory like this? Yeah, you had a question, somebody? Okay. So let me just give you the way it's done. But you may not buy what I'm saying, but the essential saddle point equation that I'm going to get at the end, you can also derive without trying to justify them. Just say, this is the graphs I'm going to sum. So in that sense, if you're happy with that, then you can ignore this motivation. Yeah.
Sorry, so we may be moving ahead, but you would get this exponent to be 2/3 again in the saddle point?
Yes, yes.
Okay.
Okay, so the idea here is the following, that you will not be surprised to learn, that you introduce a bunch of random couplings. But these couplings will be random in some flavor space, not random in position. So you're maintaining all the symmetries, including you can maintain the spin inversion symmetry and all of that. You're just looking at a bigger problem with more indices. And the Yukawa couplings will become random. So this G will become random function in flavor space. So this is what you want to do. So I'm going to run, the first term will be the same. L sub f will be sum on alpha, and alpha will go from 1 through n. Momentum is still perfectly well defined. And L of phi will also look exactly the same, except phi will now have n labels too. Let me go ahead, gamma, runs from 1 through n of the same, del x phi alpha squared plus, in fact, yeah, none of this will. There are many choices you can make. They all give you the same answer. So the U term doesn't really matter in the end. But anyway, okay. So you just take n copies of the phi field. And then you have some Yukawa coupling. Again, it has the same structure in space and time. But now you put a 1 over n in front of it, and you sum over alpha, beta, gamma, and it'll be phi, gamma, f dagger alpha. Well, okay. The sigma z I'll just drop because it doesn't matter in the end. And then I'm going to write this as G alpha, beta, gamma. Okay, so you have n flavors of fermions and bosons. You can even make them unequal, n and m flavors if you want. But simplicity, let's just take n. And so you have n cubed coupling constants. So here's another theory. I mean, it's the same symmetries and same structure as this theory. It's just more complicated. It has many different coupling constants. Okay. Now, if life was simple, the results won't depend on all this detail.
Can you explain the symmetries better? The original system has a Z2 symmetry under which phi flips sign, and F alpha, in the indices alpha and beta are exchanged.
Right. Okay. So
here
this theory,
I don't see that.
Right. So at the cost of some extra indices, you put some extra index on the G, you can make the symmetry explicit. The theory, I'm going to look at a theory that doesn't really have the symmetry in every realization of G alpha, beta, gamma, but it will statistically have the same symmetry. This is just for simplicity. If you want me to keep the symmetry in every realization, I can. It won't change anything. So just, okay. You'll see in a few minutes, it won't matter. Okay, so I'll define what these G alpha, beta, gamma are. There's some ensemble of G alpha, beta, gamma I'm going to look at. That ensemble will have that symmetry. Or I can make it explicit in every member of the ensemble by adding more indices, but let me not do that. Yeah. Sorry?
Just to confirm, different phi alpha are decoupled, right? Or like,
yeah, they're decoupled. They're coupled only through their coupling to the fermion.
They're just coupled to the fermion.
Yeah, I mean, yeah, let's do it that way.
Okay.
If you actually, if you feel better, you can couple them by making this square. This term actually won't matter in the end.
Oh.
Okay.
So, excuse me, in the original SYK model, as you said, there was the physics actually asked you to look at random couplings. Is that true in models?
Well, so yeah, I think that's the point I was going to make. So I mentioned all these systems, U1 gauge field, SU2 gauge fields, all kinds of symmetry breakings, Ising, point group, whatever. So they've all been studied, as in the end, they have essentially the same critical behavior. So it's a reasonable hope, not proven, that all of these models, so you have some space of n cubed couplings, and maybe that most of that space flows to the same fixed point. So the low energy behavior of all these theories, independent of the values you pick for G alpha, beta, gamma, is the same. That's what I'm going to assume without proof. But I think it's a very reasonable assumption. And once you assume that, you say, well, okay, in that case, I don't want to study every theory. I don't care. I only want the infrared behavior. And if the infrared behavior doesn't depend on your bare coupling constant, why don't you just average over it? So that's the point of view I'm going to take. And that leads to a controlled way of analyzing this problem. Yes?
So, the original problem was a way of thinking about phi going to minus phi.
Yes.
Up minus down amount of fermions going to.
Okay, since I'm getting so many questions, what I can do is I can introduce another index. Let me call it A. So A going from plus and minus. And then I can put a sigma Z A, and then A here and A here. Yeah, you can just do that, and then it'll be all fine. Yeah, I can, but I just want to spare myself all these indices, so I'm not doing that. As you'll see, the results only depend on the second moment of G. And so we just change this. And G, the value of G will drop out of the answer in the end. Whether G is positive, negative, doesn't matter. It only depends on G's second moment of G, and that determines the leading critical behavior. Okay. All right. So now what do we do? Well, we do exactly what we did with the SYK model. I have to define the ensemble of G's, and then you'll see and then it just becomes a task in perturbation theory in powers of G. You get some set of equations. Those equations are not new. Those equations are sometimes called the Eliashberg equations. And it's been a long-standing problem, despite their use over decades. How do you justify them? Well, I think this is the only way to justify them, by looking at an ensemble of problems. Okay, so I'm going to look at, and I should not write below some line here. Okay, G alpha beta, I'm going to look at an ensemble where G alpha beta gamma average is 0. And I'll also, they're independent variables, just like in SYK. And the mod squared, I'm going to take them to be complex, obeying some hermiticity conditions, will be G squared. All right, so now you just do exactly what we did for the SYK model. So I'll skip a lot of steps. Expand in powers of G, average graph by graph, and then figure out what are the graphs that survive in the large N limit. The only place N appears here is in the 1 over N here, and in the sum over these indices. All right. So you forgive me if I just write down the answer, because the answer is very, very similar to the kind of answer you get for the SYK model. Let me write down schematically. So the fermion-Green's function, G of omega and K, will be something like this, minus some self-energy of K and omega. And the boson-Green's function, which I call D, this K can be arbitrary, this K will be small, will be 1 over, I'm going to work in imaginary frequency. So let me put the I's over there. So that'll be minus omega squared plus K squared minus some self-energy, which will be pi of K and I omega. Okay, so this is just a definition. This is the Dyson's equation defining the self-energies. Okay, so what is the equation for sigma? Well, it's very simple. Sigma in the large N limit turns out to be the following graph. So let me say orange is the fermion. So sigma is equal to, and then I'll make yellow the boson. So this will be the boson. Okay, and this will be the full Green's function, just like it'll be G and this will be D. Okay, so that's the answer, and you get a G squared here. And what's pi? The boson-Green's function. Well, pi is equal to, again, the simple bubble. And this is now the full G, and the full G, and another G squared out front. And that's it. So the only novelties beyond perturbation theory or the self-energies is you make all of these fully self-consistent. These are full Green's function D, G, D and G and these. So if you write it out more explicitly, this is again, just like the SYK equations, much easier to write out in position space, which is what I'll do. And then, you can take a Fourier transform as needed. So in position space, this tells you that sigma of R and tau is equal to G squared times d of r and tau after the Fourier transform times g of r and tau. And pi is minus g squared of g of r and tau and g of minus r and minus tau. Okay. So these are the four equations for two functions. That come out in the large N limit, and this is the complete large N limit. Okay, so and these equations, as I said, are not new. They're, although Eliashberg wasn't studying this problem, at least in the Russian literature, it's traditional to call these types of equations the Eliashberg theory or the Eliashberg equation, where you just take these very simple one loop diagrams for the self energies and make everything self-consistent. So why did I bother with all of that nonsense about random couplings? Well, these are the equations that pop out when you just take the large N limit of that theory. And why is that useful? Because if you can now do the analog of the G sigma theory for the I mentioned for the SYK model, you can do the same thing here. And that gives you a very systematic way of understanding how to do corrections beyond the large N limit, which is something, despite decades of study, there was no understanding how to do it and how to justify the Eliashberg equations. So this gives some justification for them. Okay. And of course, they are very similar to the SYK equation where you had sigma, sigma was G cubed. Here, something like, you can think of D as G squared. So you put that D in here, you get sigma as G cubed, roughly. But you have also noticed that the Green's function is much more complicated. They're not just a function of frequency, they're also a function of momentum. Yeah.
So this large N is like large N in both boson and fermion.
Yes.
In which sense it's different from the Sangsik large N.
Yes, that's right.
Then can you just say once more, why did you need random couplings if I did large N in boson and fermion in the same sense as Sangsik? Yeah. Why wouldn't I get the same thing without
you
the
wouldn't. I mean, so if you just say make the fermions large N, which is what is easier to do, you integrate out the fermions, and then you get an action with an N in front of it. But that action has only a single, you can't have N fields in it. The number of bosons cannot be of order N. It has to be of order 1. Okay. So that doesn't work. So the only way to do systematic large N where both fermions and bosons are N indices is to have random couplings. I don't know how else to do it. Yeah. When you have random couplings, then both fermions and bosons are treated at an equal footing. And that's actually crucial to get the physics right. Okay, Sumati, you have a question? Okay, sorry.
Subir,
yes, Tom.
If you had a SUN gauge theory coupled to fermions in the adjoint representation,
yeah,
you have the counting of bosons and fermions that you want.
Yeah, well, but you won't have the random couplings there. Yeah.
Right. I don't think that leads to these equations.
Well, if you sum these graphs, suppose I take your favorite theory, and I just tell you to compute these two graphs with the appropriate indices over here of the SUN generators and everything else. You compute these graphs, you will get essentially the same equations, but perhaps some of the numerical factors here will be slightly different.
Right, okay. But I don't think the 1/n corrections would be small.
Well, well, let's see. About which state? If you had a dilute gas, you're right. But in a dense gas with a Fermi surface, I believe that's quite stable. Yes.
I mean, the standard statement is you have to sum all planar graphs.
No, but okay, but that's not the 1/n expansion I'm making. I would have to take your SUN theory and supplement it with some additional random couplings to justify this 1/n expansion. But I'm saying you can do, you could take your theory and just sum these two graphs. I agree that these two graphs are not justified by the SUN large N limit. They're justified by a different large N limit. But my claim is that these two graphs have the essential physics, even for non-abelian gauge field in the presence of a Fermi surface, because that's a deconfined state in the sense of the low energy singularity. And you'll see that value of G squared is going to drop out of a lot of interesting things. Okay, there's another thing another objection you may have made, that there are these momentum dependence in the vertices for a gauge theory. I'll come to that. That also doesn't matter in the end. There's no momentum dependence here. It's a non-gradient coupling. And so these equations are very simple. It turns out once you have a Fermi surface and you take the right low energy limit, all those momentum dependencies don't matter. You will get the same low energy behavior. That I'll probably show next time.
One question. So
yeah.
Where did the information about the finite DOS go into this?
The finite what?
The density of states, the finite density of states of the fermions.
Not yet, not yet. I'm coming to that. Thank you. So now our task, okay, the task for the rest of the lecture, I think, yeah, definitely the rest of the I will not finish today, is to solve these four equations, okay, in the low energy limit for some dispersion E of k, which vanishes on some contour in momentum space. So all you give me is the shape of the Fermi surface. And if you want, you can give me the value of G, but it won't matter. And I want to solve these equations. Okay, that seems impossible. You may be tempted to put it on a computer. In fact, you have, and it's still very, very hard because you've got both K and omega to worry about. And this Fermi surface with a strange shape. But what I'm going to argue is that just like in the SYK model, we could analytically obtain the leading behavior, the 1/squared of omega and its prefactors could be obtained analytically. Similarly, we're going to obtain an exact solution of these four equations, like them or not, in the low frequency limit, the low energy limit. So we'll obtain exact solutions of these equations. So that's the next task. In the low omega limit for small omega. And of course, near the Fermi surface for the fermions, and small k for the bosons, right? So there's in fact an exact, it's kind of surprising that there is an exact solution, but there is. And it relies on some very nice properties of Fermi surfaces, which is where the finite density of states of Fermi surfaces will come in. That kind of trickery will absolutely not work in one dimension. So we'll obtain the solution of these equations. Okay, so there, of course, this is not the full solution to the problem. There are 1/n corrections and what else. We'll obtain the solution of these equations, and then from that, those equations, you will also see, I think quite easily, why, if you had other more complicated couplings to the fermions, why none of that matters either. Okay. All right, so for now, we are mathematicians and we're going to solve these four equations. Okay. So let's just begin by the very simplest graph, which is where actually all of the important features emerge. So what we're just going to begin with is just evaluate pi with using G naught. So that's a old-fashioned calculation in every textbook consolidated physics, but I'll do it in a slightly different way that will highlight some very important features. Okay, so we're just going to compute pi. Step one would be to compute pi using G naught. Now, of course, G is not G naught. It's got a sigma in it. Okay, but we'll come back to what the effect is of sigma is on this calculation later. All right, so pi then of omega and k. Let me call it Q, I think. I want to separate Q space from K space, would be minus sum on omega and K. Okay, I'll use the notation on notes. I'll call this capital omega and Q, sum on omega, or I sum on K and integral, well, okay, it's all right. 1 over I omega minus EK, and I omega plus omega minus EK plus Q. All right, that's just the bubble diagram with the bare Green's functions. Now you can do the sum over omega, and then you get the Lindhard function, f of EK minus f of EK plus Q, and I'm sure I will not try to get the sign right. Okay, I omega minus EK plus Q plus EK. Okay, I probably wrote this down earlier in the course. This is the famous Lindhard function, which goes into the dielectric constant of a metal. It's the same thing. Okay. So we want to evaluate this at low temperatures or zero temperature. And in general, of course, many things will depend upon the precise dispersion, but we're not interested in a lot of that. What we want to compute is the imaginary part of this. Imaginary part of, for real frequencies, omega and Q, as Q goes to 0. So Q is small, and I want the imaginary part. Okay, and there's a sum over K here. So I just take the imaginary part of the denominator, but then IHR in there. And so I'll get D2K of F of EK minus F of EK plus Q. And the imaginary part will give me with a minus, but the sign is random, times delta of omega minus EK plus Q plus EK. Okay. All right, so now Q is small. So I can also go ahead and expand this numerator, the difference of Fermi functions. So the numerator, which is F of EK minus F of EK plus Q, well, that's approximately equal to EK plus Q minus EK times minus of dF of EK. That's just the derivative expansion. And this at low temperature, we know is a delta function. Okay, so I put that delta, so I have a very simple integral, which is just the product of two delta functions, minus pi d2k. Also, you can do this in any dimension, f. So this thing becomes EK plus Q minus EK, but because of this delta function, that's equal to omega. So I just put a factor of omega to make my life simple. And then I have this delta function. And I have the other delta function. Okay. All right, so I want also the low frequency behavior, and omega and Q goes to 0, and omega goes to 0. So omega has gone to 0 already, and there's already a factor of omega out front. So maybe it's reasonable to just ignore this omega. You can put it and check that doesn't matter in the end, no trouble. Okay, so we just ignore this omega for now. Let me put a dash through it. Okay, so whether you ignore the omega or not, you have two delta functions, and you have a two-dimensional integral over K space. So the only solutions will be discrete points. Okay, so if here's our Fermi surface with some strange shape, I'm going to assume it has inversion symmetry mostly. That's about it. And say my Q vector, it has some direction. It's small, but maybe it's pointing in this direction. So that's Q. So where will I get a contribution to this imaginary part? Well, so of course, one equation I have to solve is EK equals 0. And the other equation I have to solve, ignoring this omega, is Q dot gradient of EK equals 0. So these are the two equations I have to solve, and then I have to do the integral. Okay, so in 2 dimensions, generically, there's only be discrete points where you have a solution because you have two equations and two variables. In 3 dimensions, there'll be a line, but let's stick to 2 for now. So which are these points? Well, EK equals 0 is just the Fermi surface. So it's 2 points or discrete set of points on the Fermi surface. And this tells you that the gradient of EK should be orthogonal to Q. Well, the gradient of EK is just a vector proportional orthogonal to the Fermi surface. So there's really only 2 points, and they're opposite each other. There's a point here and a point here. Okay, so here the gradient is this way. This is grad of EK. And then here, of course, it's that way. And they are orthogonal to Q. So the entire contribution to the low frequency behavior of the density correlation function comes from these pair of antipodal points. Yes? Because I want to look at the leading behavior as omega goes to 0. And you already have an omega at front. So it's already linear in omega. So any corrections will be higher order in omega. In fact, it doesn't make a correction at all. But just to make my life simple. You can put it back in. That's a homework problem for you. That's right. That's right. Yeah. But I already have an omega out front. So that's why. Okay. Yeah, maybe I can clean it up and not make that approximation. And when I was working out the notes yesterday, I removed it. Okay. But this conclusion is still correct. The entire contribution is going to come from these 2 points, which are whose normal is orthogonal to Q. Okay, so in fact, I can do a theory of these 2 points. Just focus on these 2. And so at this point, there'll be some Fermi velocity, and there'll be some curvature. You will also need to include the curvature, as we're going to just see in a minute. So I'll choose some coordinate system. I'm going to call this direction ky. I'm going to measure momentum. Ky is parallel to the Fermi surface, and kx is perpendicular to the Fermi surface. And this point I'll call k naught, and this is minus k naught. And I'm just going to say that by dispersion E of k, which is some very complicated function, will be some Fermi velocity, which will be a function of k naught, some function that I don't know, depends on EK, but linear in kx. And then the other direction would be a curvature, kappa, which is a function of k naught, over 2 times ky squared. So in this direction, it's linearly dispersing. In the other direction, it's quadratically dispersing. Has to be a minimum in that direction, of course. And here it goes through 0 in this direction. So kx can be negative or positive, as can ky. And these functions, Vf and kappa, are some coefficients that will vary in some way around the Fermi surface. And in fact, they will be renormalized. They're not, they will be renormalized by various terms, even in these equations. So when I say I can solve it exactly, I mean I can solve it exactly in terms of the renormalized values of these parameters. So I'm just going to regard these Vf and kappa as known parameters at each point on the Fermi surface. And that's really all I'll need to know. Okay. All right, so now that I take the dispersion at these 2 points, I can just plug it in here and evaluate the integral. And you get the famous answer. Of course, every textbook has that answer, although perhaps not this way of deriving it. Okay.
So I have an intuitive question here.
Yes.
The original fields, how many momenta do they depend on?
Sorry, which fields?
So the original fields started with, say, f or phi. They were functions of 2 momenta.
Correct.
And now we have 3 variables. So we have both k0, kx, and ky.
Well, kx and ky are the fermion momenta.
Yes.
And q is a vector in arbitrary direction, which is the boson moment. Q
Right,
is the momentum of
k0.
phi. Huh?
I thought k0 is the vector on the Fermi surface.
Well, k0 is the location. So you give me a q.
Yes.
You pick the momentum q of the scalar, and given the momentum q of the scalar, that fixes k0. K0 are the 2 points in the Fermi surface whose tangents are orthogonal to q. So k0 is fully determined by q. So yeah, so the independent momenta are q for the boson and kx and ky. Well, some general k for the moment for the fermion. Now, what I'm going to do is I haven't done it yet. Right now, I'm just saying I'm going to do this integral that's up there. And that integral will have 2 contributions, one from the point k0 and one from the point minus k0. And I'm just going to do those 2 integrals in 2 separate steps. Right, okay. I'm just doing that integral on the top. And the integral has contributions from 2 points. All right, so that integral, pi of omega and q, I can approximate to 2 small integrals, one here and one there. And they have the same value, so I'll just put a factor of 2 and take only the top point. And now I'm integrating, maybe I should call it k tilde. So yeah, so when I use the convention I'm following is when I write components of a vector, I'm measuring them from the point k0. And when I write a vector like this, I'm measuring it from 0. Okay, so k is equal to k0 plus kx, ky. Okay. All right, so now I just do that integral. That's really very simple. Now since it's just a delta function, I only need to take the leading order term in both directions. So delta of ek will give me vf kx plus kappa over 2 ky squared. And delta of ek plus q minus ek will give me delta, and you can put the omega here if you want, but I won't. Ek plus q minus k would be vf qx. No, sorry. It'll be, hold on a second. So now the point is that q is exclusively in the y direction. I chose the point q0 so that q will be in the y direction. That's the coordinate system. So at this point, q is just 0, q. Okay. So then I only need to take this guy into account. So it'll be kappa times qy ky plus kappa over 2 qy squared. Okay, so these integrals are very easy to do. You do the integral over kx, you just pick up a factor of 1 over vf. You do the integral over ky, you pick up a factor of 1 over kappa qy. So this is equal to 2, and there's a 4 pi squared. And I probably forgot that factor of pi out front. And then I will have the omega that was over there. And you could put the omega in here too, it won't make any difference. So the omega over vf times kappa times qy. So that's the answer. And in fact, this is just mod q, you can see in general, it's mod q. So that's what it is. With the sign, I think, okay. So that's the polarization. This is the omega over q. This is sometimes what's called Landau damping in a Fermi liquid. Computed in many different ways. This is the way that's most illuminating for our purposes, because it highlights that the entire contribution comes from this pair of antipodal points and is associated, basically with zero energy fermionic excitations, which move tangent to the Fermi surface. You look at the second delta function, that's where the omega minus ek plus q plus ak, that's telling you you're absorbing energy omega by an electron moving from k to k plus q, and q is tangent to the Fermi surface, not orthogonal. And that's completely dominates this process, and this is crucial to everything. Okay. And this, and there's some additional q dependence that's hidden here, in the sense that once you pick the direction of q, that picks as q and k naught, and vf and kappa depend on k naught. So there's some very complicated q dependence, but we don't, that's some smooth q dependent. We don't worry, we just ignore it, because that's something that gets normalized, something you can measure in experiments where you measure the Fermi surface, so fine. Okay. All right, so that's great. And now the remarkable result is that under certain conditions, which I will now specify, and I unfortunately have erased the form of the full equations, this result is basically exact. It doesn't get renormalized. Apart from renormalization, the values of VF and kappa, even if I use the full Green's function. Okay, so that's our next task. So that's, we just evaluated the pi using G naught, and now I want to evaluate pi using the full G. And then we'll see that there are no corrections. Okay, so that's the surprising part. Again, it's, I'm sure, known to many people, but it's always hidden under pages of very complicated calculations that it's rather obscure to anybody not in the field. But okay, I'll try to clarify it. Okay, so now we're going to compute pi using G. All right, this is not true in complete generality. It's going to make a certain assumption, which we will then have to verify is self-consistent. So we're going to compute pi using G, not G naught. So we're going to assume, and this is an assumption which will be later seen to be self-consistent, that the self-energy of the fermion, sigma of chi and I omega, has basically two pieces. There is some smooth momentum dependent part. This is smooth. And then there's a part which depends only on frequency. Let me call it sigma 1 and sigma 2. And this is singular as a function of frequency, as a function of omega. As we'll see, it also has some momentum dependence. People often say it's momentum independent. It's not. It will have some momentum dependence, but that momentum dependence will entirely come from the momentum dependence of VF and kappa. So we don't have to, yeah. So in that sense, it's, let me put it in quotes, and smooth and smooth K. So it's kind of just depends on the location of the point K naught. Yeah, so we're going to compute sigma, say, on the Fermi surface near K naught. The answers will depend on K naught a little bit, but not in some essential way where I have to worry about it, and it changes any singular behavior as a function of omega. Okay, so with this assumption, my Green's function, I'm just going to write near K naught. So G as a function of omega, and now I'm near K naught, so Kx, Ky. I'm going to write it as I omega minus VF Kx minus kappa over 2 Ky squared minus sigma of I omega, which is just the sigma 2, and I'm dropping the 2. And I'm also dropping this because that can be absorbed into the normalization of VF and kappa. So I assume that's already been done, because in practice, you don't know these numbers, you just measure them, and the measured quantities already have the self-energy corrections in them. Okay, so this is the G I'm going to take. And now I'm going to insert this object into there and compute pi again. So I'm going to go through the same calculation, but I'm going to do it slightly differently and show you that the answer is actually independent of sigma. Doesn't depend on sigma. I'm going to get exactly this answer when I do this computation with the full G in there. And I have 10 minutes left. Okay, probably won't get to the end of it, but that's where we want to go. So no, this is where we really get into some nitty-gritty of solid state physics and many body theory with these horrible integrals that don't have Lorentz invariance that immediately turn any particle physics off, but they have their own elegance. And so you have to know how to do these integrals carefully. And they can be done. And in fact, the answer for pi will be exactly the same. So that will be that's halfway towards solving the full Dirichlet equations exactly. All right, so I can just make the changes right here. So I can put a sigma of omega, sigma of I omega, arbitrary function, and EK will now be whatever that expansion is, I omega plus omega minus EK plus Q minus sigma of I omega plus omega. Okay. Now, what we did last time was that we did the frequency integral, and we got this famous Lindhardt result, and then we just took its imaginary part and straightforwardly evaluated it. Now, if you want to follow that route, you immediately hit a roadblock. I can't do the frequency integral because I don't know what sigma is. So you can give up. But now I have now decided that I'm actually only interested in the contributions near the Fermi surface. After all, when I did the calculation honestly for the imaginary part of pi, everything was just dominated by near the Fermi surface. Of course, the real part of pi has contributions far from the Fermi surface. And if I really wanted those contributions far from the Fermi surface, then all hope is lost. You have to solve the whole equation on the computer. But if I just want the imaginary part of pi and see that this result, which is fortunately been erased. Yeah, well, it's up there. That's the imaginary part. There should be an imaginary in front of that. Sorry. Then what I can do is I can expand this near the point K naught. I can do a similar calculation near the point minus K naught. That'll just give me a factor of 2. So I'll put a factor of 2 here and expand this minus VF kx plus kappa over 2 ky squared. And similarly here. Minus VF kx plus kappa over 2 ky plus q squared. Remember, I chose k naught to be orthogonal to q. Okay, so that's what I have. And now at least it's easy to do the kx integral. It's almost looking relativistic. Okay. So I have the only place kx appears here is linear. Only place it appears here. And so I can do the integral. Okay. So if I and it's convergent because it falls off as 1 over kx squared. So this is basically the integral about the chiral fermion in the kx direction, which is the only contribution you wanted to include when you were doing this chiral Luttinger liquid type theory. All right. Okay, so now if we look at this integral, you can do it by the method of residues. So if this is the kx axis, then this thing has a pole, and the pole, if I ignore the self energy, it'll depend on omega. If omega is positive, the pole will be in the upper half plane, and if omega is negative, it will be in the lower half plane. Now, one thing we'll find, and this again you check, and it's actually required by analyticity of the Green's function, that the sign of sigma is the same as the sign of omega. If this is positive, then this is positive, and so on, with the I out front. So the analyticity property is not changed by the sigma. So if this omega tells me I'm in the upper half plane, the pole will still be on the upper half plane. And similarly over here. So for this integral to be non-zero, I have to have one pole in the upper half plane and the other pole in the lower half plane. Otherwise, it's 0. Okay. So you can do the integral exactly, and then you get the following result. Where's my glasses? Okay. What do I do with my glasses? All right, well, I'll have to squint. Everybody know where my glasses are? Okay, so you do the integral and you get the following answer. So again, I will leave all well, there's a minus I, there's also a g squared, which I forgot. Okay, you get a 1 over VF. Then you'll still have the sum over omega, the omega, the integral over ky. And then you'll get sine of omega plus omega minus sine of omega. So that's required for the poles to be in the opposite half planes. And the sine of sigma is the same as sine of omega divided by I omega plus sigma I omega minus sigma of I omega plus omega minus kappa over 2 qy squared minus kappa qy ky. Okay. Okay, so that's completely well defined. Where I have just assumed, however, I have made an approximation that I've assumed the dispersion is linear in K. That's not true in general. And if you want the full contribution from outside the Fermi surface, then you do have to worry about that. Okay, and now I'm still not able to do the omega integral, but I can do the ky integral. It's linear in ky. Now, at this point, you might also worry that it's not convergent at large ky. This goes as 1 over ky. But, well, there's various answers to that. One is that, when you symmetrize from minus infinity to infinity, the divergent passes on two ends cancel. The other argument is that we're only interested in the contribution at low energies, or the imaginary part of pi. In this case, you can just take the imaginary part, which is convergent after analytic continuation. So basically, the kind of integral you're faced with here it's just dk dky over 1 over some ky plus I times some constant. So what is this? Well, that's just equal to sine of A, basically. All right, so when you do that integral, you get the following answer. So this thing becomes, after you do the k integral, it becomes, all right, I'll keep all the factors here, 2 kappa VF, and what is that? Q, you get a QY from this QY multiplying the KY, and you will get d omega sine of omega times sine of omega plus omega minus sine of omega, or something like that. Yeah. Okay. Finally, I have the integral I care, that I can evaluate omega, but the self energy just dropped out completely because I just needed the sign of this object. And so this thing turns out to be, you do this integral, you get a factor of omega, and it's exactly what I had before. Okay. I think that's a good point to stop, but that's the remarkable answer, that this Landau damping omega over Q factor is independent of any frequency dependent self energy. Okay. And of course, it is dependent on the self energy in general, but all of that can be absorbed into the definitions of kappa and VF. There's nothing else. All right, so that's probably as nitty gritty condensed matter as anything gets, all these complicated integrals. Yeah, all right, but it illustrates a very important point. Yeah.
How do I understand this result, that why doesn't this frequency dependent part?
I have to think about that. I mean, it's partly related to the fact that you're measuring some kind of density correlation function, and there's no renormalization of density operators. If you think in terms of quasiparticles, then it's easy to see. You're just thinking some renormalized quasiparticle absorbing energy. But it's actually much more general. It doesn't even require the existence of quasiparticles. It's a much more general result for arbitrary frequency dependence of sigma. Yeah. I think the key, what it relies on, the fact that you have some incoherent set of excitations, but they don't depend on momentum. The only momentum dependence is the bare energy. So when you're absorbing, when the density fluctuation is emitting energy into whatever these incoherent excitations are, the momentum kind of fixes how much energy is absorbed. I think that's probably one way to think about it. But I'll try to, that's a good question. I wish I had a better answer. I'll think about it. Okay. All right, so that's the first step, and actually the most difficult step for solving the algebraic equations exactly, showing you that there's a simple exact result for at least the scalar field Green's function, the imaginary part of scalar field Green's function at very low energies. And it's a very singular term. The scalar field propagator now is something like minus omega squared plus q squared minus this omega I omega over 2 kappa VFQ. So this is extremely singular at small frequency and momentum. You can forget about this term completely. And this basically overdamped. So you might think you had a particle, a linearly dispersing particle. That particle is totally overdamped by this, and it's because of its coupling to the Fermi surface excitations. And the important point here is I've shown you, I mean, this is not new, everybody knows this, that this Landau damping factor is independent of, is also true when you don't have quasiparticles. That's what this calculation shows you. All right, okay, so, and it's this Landau damping to answer some of Tom's earlier question. The gauge boson will also undergo this Landau damping, and that makes the physics of gauge field totally different from what you're accustomed to. This fact that the gauge boson is completely overdamped. Yeah. Okay, so we'll have one last lecture next time. See you on Friday.